Okay, so here's an example. Let's take a look at this case. So in this question, a 0.1 meter long alumina Al2O3 furnace tube is heated from room temperature all the way to 1000 degrees C. We'll assume that the tube is not mechanically strained under this condition, so there's no mechanical forces or strain built in. And we're asked to calculate the increase in the length by applying this heat. So we are to apply that alpha equation that we saw a moment ago. So again, that alpha equation was 1 over L dL by dt, change in temperature differential. Okay, so take a minute to try this question and resume the video when you've had a chance to evaluate your answer. We'll see what you got. Okay, so we said a moment ago that we were going to use alpha is equal to 1 over L dL by dt. And to answer this question, we must make an assumption. So we'll assume that there's a linear thermal expansion effect here, okay? So assume linear thermal expansion, which allows us to rewrite this equation as alpha is equal to 1 over L delta L by delta T. Okay, and now we're asked to, of course, determine the length from this heating. So in other words, we have to solve for the delta L. Okay, so what we'll have here is that delta L is equal to alpha L delta T. After doing so, and we'll need some additional information that was provided on the previous slide. So we're going to need the alpha value for this material, so this alpha value for alumina. So we'll go to the previous slide and look for that. So that alumina was Al2O3, and so we see that material listed right here. And so we're using the 8.8 millimeters per millimeter to the degree C. Okay, so millimeters per millimeter degree C. Okay. We're also given the original length, so that was 0.1 meters at the low temperature condition. And we need to know the delta temperature. So here in this case, the change in temperature is going to be delta T is equal to 1000 C minus 25 degrees C. So that is 975 degrees C for delta T. And of course, L is equal to 0.1 meters. And you can see based on the alpha that it would make sense to transform L into millimeters. Okay, so we'll put a conversion factor here, cancel 1 meter. Hang on here, sorry. One meter is canceled by 1000 millimeters, and that gives us 100 millimeters for L. Okay, so at this point you can simply start applying the values and looking to cancel. So 8.8 millimeters per per millimeter degree C times the 100 millimeters times the change in temperature, 975 degrees C. We can just look to make sure that units are canceling. So degree C is going to cancel degree C. Millimeters is going to cancel the millimeters in that alpha, and we'll end up with a delta L in millimeters. And so at this point you should get roughly 0.858 millimeters for the change in length of this material. So that is the increase in length is represented by delta L here. Okay, good. Okay, so moving on. We'll transition now into failure analysis. This is chapter 8 content. So we'll preface this with some ideas like we've had before, that it's very difficult to realize the mechanical properties predicted by simply extending bond energy information out to the bulk sample. So for example, for a perfect material that has no flaws, you would expect a stress versus strain curve to be much higher. That is, the ultimate tensile strength of the material, the highest point on the curve, would be much higher than we can actually realize. So in a material like a glass, for example, that was perfect, you might predict the highest data point to be arbitrarily this high. However, when we do our best to carefully produce the best piece of glass possible, we would ultimately get a data point that is not as high as that. So that is the amount of stress that we can put on the material before it fails is going to be less. And likewise, when we look at kind of typical ceramics or typical glasses, you can see that these more average materials are even far worse than that. Sometimes tenfold lower in their ultimate stress value than predicted. Okay, lots of other people looked at this idea, and so even Da Vinci 500 years ago was able to observe something similar. So his experiment's kind of interesting. Let's read what he did. In the experiment, a wire of a given thickness and length was used to suspend a basket. This basket ended up slowly filled with sand. Okay, so let's see here. So here's that basket, and here's the wire in question right here. And he was to adjust the length there. So this basket was slowly filled with sand, fed from an adjacent hopper. You see that hopper right here. And when the wire suspending the receiving basket would break, automatically a spring would close the hopper and the basket would fall a short distance, permitting the sand to kind of be caught without loss from the basket. And ultimately, the sand in the basket could be weighed to establish the tensile strength of the wire. And so what the observation was, the longer the wire, the smaller the load for failure. And this, if you recall, goes against one of our ideal thoughts here from chapter 6, that the stress value, sigma, was only dependent on the cross-sectional area of the material under no load. And so here, the ultimate result here suggests that the longer the wire, the easier it is to fail the material. So something more is at play here. And so what's at play here is that there are flaws in the material, and that these defects or flaws cause premature failure. So the longer the wire, the more flaws we might have, the more opportunity for a flaw along the length of that wire. Okay, so with that idea, we need to now think more about real materials and accommodate the idea of flaws in those real materials.